Hi everyone. In the last few lectures, we have discussed about the spectrum of an operator and some examples and properties of the spectrum. From now onwards, we are going to discuss about representation of operators. So today we are going to start with a special class of bounded operators, namely the compact operators. To start with, let us start with the Hilbert space H. Let H be Hilbert space and X and Y be fixed vectors. So we can define an operator T from H to H by T of Z as inner product Z with X multiplied by Y for every Z in H. We can easily show that T is a bounded linear operator. So check that T is bounded linear and range of T is spanned by single vector Y. That means it's a one-dimensional space. So such an operator we call as rank 1 operator. So T is a rank 1 operator. Here rank is nothing but dimension of the range of the operator. Okay. Now we can ask the following question. Suppose we have a rank 1 operator. Can we say that it is in this form? The question is the following. If T is a rank 1 operator, can it be represented as in star? So let us call this equation as star. Okay, in fact we can do that. So since range of T is one dimensional, it is spanned by single vector. So let us take range of T is span Y, where Y is in H is fixed. Then we can write Tx, we can write as from alpha suffix x y for every x in H, and alpha suffix x is a complex number depending on x. Okay, now without loss of generality we can assume that norm of y equal to 1. Assume that norm y equal to 1, otherwise we can normalize it. Then we can look at inner product Tx with y is nothing but alpha x, because inner product y with y is 1. So therefore alpha x we can write, this alpha x we can write as x T star y. So hence we can write Tx is nothing but x T star y inner product of x with T star y multiplied by y. So we can call this vector T star y as some z. So this is exactly in the form that we have discussed earlier. So we can say that all rank 1 operators are given in this way. Now we can generalize this to rank n operators also. So definition, let T be a bounded operator on H, then T is said to be of rank n if dimension of range of T is exactly n. Okay, now how can we represent rank n operators? So let us try to discuss in the same way that we have discussed. So let us take x1, x2, so on xn in H, and y1, y2, so on yn coming from H. Then define T from H to H by T of Z as summation j equal to 1 to n inner product of Z with xi multiplied by xj multiplied by yj. Okay. Now we can easily see that T is bounded, and we can say that rank of T is less than or equal to n, because some of the vectors yj's may be linearly independent. If they are linearly dependent, if they are linearly independent, we get rank of T to be exactly n. Okay, so this is a rank n operator whose rank is less than or equal to n. Now if you have an operator of rank n, can we say that it is given in this way? So in fact we can prove the result. Let T be a bounded linear operator on H, and rank of T is exactly n. Then there exist vectors x1, x2, so on xn in H, and y1, y2, so on yn in H, such that T of Z we can write as summation j equal to 1 to n inner product Z with xi multiplied by xj multiplied by yj for every Z in H. Okay. So the proof goes in the similar lines of the earlier rank 1 case. So let us look at the proof. So assume that since rank of T is n, so range of T is spanned by n vectors y1, y2, so on yn. Okay. Then we can write, hence we can write T of Z as summation alpha j yj j equal to 1 to n. So in fact we can choose y1, y2, so on yn to be orthonormal. So y1, y2, so on yn is orthonormal, because once they are linearly independent, we can apply the Gram-Schmidt process to get an orthonormal set. So let us call them as y1, y2, yn again. So then we can easily find out what is alpha j. Alpha j is nothing but inner product tz with yj. So this can be written as inner product of z with t star yj, j equal to 1 to so on n. Now you can write xj as t star yj, j equal to 1 to so on n. Then we can get the required representation of t in this way. Now we can actually write down this result for operators between two different Hilbert spaces, h1 and h2. In that case, this y1 y2 so on yn belongs to h2 and x1 x2 so on xn belongs to h1. Okay, so this is the structure of rank n operators. So we say an operator to be finite rank if the rank is finite. A bounded operator is said to be a finite rank operator if rank of t is finite. Okay. That means range is finite dimensional. So we usually write so here we can take t from h1 into h2. So we denote set of all finite rank operators by script f h1 h2, set of all bounded operators from h1 into h2 such that t is finite rank. Okay, now we can easily show that if t is a finite rank, then alpha is a complex number, alpha t is finite rank, and if t1 t2 are finite rank, then t1 plus t2 is also finite rank. So it is easy to check that this f h1 h2 is a vector subspace of B of h1 h2. Okay, now let us try to observe the particular nature of these finite rank operators. Since the range is finite dimensional, if you look at the closed unit ball in the range, then that is it is compact. So if you take a finite rank operator, so let us take t to be finite rank operator, and so B the closed unit ball of h1, here 1, then we can say that T of B is pre-compact. Okay, but not every bounded operator satisfies this condition. For example, so let us take let H be Hilbert space of infinite dimension. Then the identity operator I from H to H given by x going to x, x in H is bounded but if you look at I of B closure, that equal to B closure, that is again B, because B is closed. This is not compact since the space is infinite dimensional. Does there exist T in B of H? So especially when dimension of H is infinite, such that T of B is pre-compact. In fact, we will show at a later stage that such operators exist, and in fact, if you look at the operator norm closure of this set of all finite rank operators, then we get all such operators. So such a map we call as compact operator. A bounded linear map T is from H1 into H2 is said to be compact if T of B is pre-compact. That means T of B closure is compact for every bounded set B in H1. Here it is in H2. Okay, instead of closure interval, we can always take a bounded set. Okay, so such a map we call it to be compact. Okay, now our next question is, what are the properties of compact operators and how to get all the compact operators? That's what we want to discuss. So far the examples are finite rank operators, and second one is bounded operators defined on finite dimensional Hilbert spaces. So set of all so your dimension of H1 is finite. Okay, because when H1 is finite dimensional and if T is a bounded operator from H1 into H2, range of T is anyway finite dimensional. Now by the earlier observation we can get the required property. So these are the examples for the time being. So later we will get many more examples of compact operators once we discuss a few important properties of compact operators. Let us fix a notation for the set of all compact operators. So we denote the set of all compact operators between H1 and H2 by K of H1 H2, set of all bounded operators from H1 into H2 such that they are compact. Now we can ask the question, is the set K of H1 H2 non-empty? In fact, we have answered this question. If you take H1 and H2 are non-zero, we can always find. So if H1 is non-zero and H2 is also non-zero, so let us take X is in H1 and Y is in H2. Now we can define T from H1 into H2 by T of z as inner product of x with z multiplied by y. So here it should be inner product of z with x multiplied by y for every z in H1. So this is a bounded finite rank operator, hence it is compact. So we can say that this set K of H1 H2 is non-zero whenever H1 and H2 are non-zero. Now the question we can ask is that is K of H1 H2 a vector space? Okay, so let us take T1 T2 from K of H1 H2 and alpha in C. So we can easily show that. So clearly alpha T1 is in K of H1 H2. Now to show that T1 plus T2 is in K of H1 H2, so we use an alternative definition for compactness instead of using the definition that we have given. Let us recall the following result from metric space theory. Let Xt be a metric space and S is a subset of X. Then we know the equivalent conditions for S to be compact. Then the following are equivalent. S is compact, S is sequentially compact, that means every bounded sequence has a convergent subsequence. Has a convergent subsequence. And third condition is S is totally bounded and complete. In most of the cases, we are going to use only the equivalence of 1 and 2. That means we are going to express compactness in terms of sequences. So we will be not using the third condition. Okay, so now we want to show that T1 plus T2 is compact. So compactness can be expressed as following: T is compact if and only if for every bounded sequence Xn in H1, the sequence Txn has a convergent sub. This directly comes from the result that we have stated now for metric spaces, because whenever B is bounded, T of B is pre-compact. So if we use this metric space result to compactness, you will get this. So this we will be using again and again. Okay, now we want to show that T1 plus T2 is compact. So let T1, T2 be compact. We want to show that given a bounded sequence Xn, T1 plus T2 at Xn has a convergent subsequence. Let us let Xn be a bounded sequence. Okay. So then Xn is a bounded sequence. So as T is compact, as T1 is compact, there exists a subsequence Xnk of Xn such that T1 of Xnk is convergent. We also know that T2 of Xnk is also convergent because T2 is compact, but we don't know T1 plus T2 of Xnk is convergent or not. Now to avoid this difficulty, we work this sequence T1 of Xnk. So as T1 of Xnk is bounded because it is convergent and T2 is compact, okay, so we work with Xnk instead of, and T2 is compact, so there exists a subsequence of this subsequence, let us say Xnkl of Xnk such that T2 of Xnkl is convergent. Now we want to we also know that T1 of Xnk is convergent. Now Xnkl is a subsequence of Xnk, so therefore we can say that T1 plus T2 of Xnkl is convergent. So this completes the proof of T1 plus T2 is compact. Okay, so we have shown that K of H1 H2 is a vector space. Now we want to ask what will happen if you take product of two compact operators. Theorem. Let T be a bounded operator from H1 into H2 and S be a compact operator from H2 into H3. Then we can say that ST is a compact operator from H1 into H3. Again we use the sequential definition of compactness. Let Xn be a bounded sequence in H1. Now T is bounded, so as T is bounded, we have that T of X1, T of Xn, this is bounded in H2. Now S is compact. Since S is compact and we know that T of Xn is bounded, so with ST, Xn has a convergent subsequence. Okay. We can also show that the other way is also true. That means if you start with a bounded operator and compact operator, If S is bounded and T is compact, we can show that ST is also compact. Exercise: show that if T is compact and S is bounded, then ST is compact. So as a consequence of these two results, we can write if you look at K of H, that is set of all, this is compact operators from H to H, set of all bounded operator, T such that T is compact. This is K of HH in fact. So for notation convenience, we write K of H. So this is a two-sided ideal in B of H because it is a vector space, and when you multiply a bounded operator with compact operator from both left and right, then the resulting operator is also compact. Hence we can conclude that K of H is a two-sided ideal. As a one more corollary, let T be a compact operator, then we can say that T star T and T star both are compact. Okay. Now we can ask the question, what will happen to the converse? If T star T or T star is compact, can we say that T is compact? Question: if T is a bounded operator from H1 into H2, is such that now T star T is a map from H1 into H1, so T star T is K of H1. Then can we say that T is compact? Okay, in fact the answer is affirmative in this case. So let us write this as a proposition. Let T is a bounded operator from H1 H2 be such that T star T is in K of H1, then we can say that T is also compact. Okay, to prove this result, we have to start with a bounded sequence Xn and H1. So proof: let us take a bounded sequence Xn. We know that T star T is compact. That means T star T Xn has a convergent subsequence. Now using T star T Xn, we should be able to show that Txn has a convergent subsequence. Now for this we have to use the relation between T star T and T, and in fact that is connected by the equation inner product T star Tx with x is nothing but non-Tx square. Okay. So we want to show that Txn is Cauchy. Okay. So let us take Mn in N with M less than or equal to N. So then we have T star. So since T is compact, since T star T is compact, as T star T is compact, there exists a subsequence x and k, a subsequence of xn such that T star T xn has a convergent, xn k convergent. Okay, so let us look at norm of T xn k minus T xn L square. So here we can take k and L instead of m and n. K less than or equal to L. Okay, so this we can write as T of xn k minus xn L inner product with T of xn k minus xn. So this is inner product T star T xn k minus xn L xn k minus xn L. Okay, now this is less than or equal to norm of T star T xn k minus xn L into norm of xn k minus xn. Now xn is a bounded sequence, so norm of xn k minus xn L is bounded by some constant. So this is let us say 2m into norm of T star T xn k minus xn L, where m is supreme of norm xn, n in m, n in n. Okay, so now from this we can conclude that since T star T xn k minus xn L goes to 0 as k and goes to infinity, so we can say that therefore T of xn k is Cauchy. Cauchy in H2, since H2 is complete, hence it is convergent. Okay, so this is what we wanted to show. Txn as a Cauchy subsequence we should write here. Okay, so this completes the proof of the fact that whenever T star T is compact, then T is compact. We can summarize the earlier result as follows. We can say that T is compact if and only T star T is compact. Now as a consequence of this, we can say that T star is compact if and only T star is compact. Now using these results we can show the following. We can easily work out, show that T is compact if and only if T star is compact. Okay. These are some of the important properties of a compact operator. Now, from the earlier observations, we can say that, so corollary, if T is compact on H, this implies T square is in compact. T square is in K of H. In fact, any power of T is also compact. In fact, we can say that polynomials of T is also compact. Now, the converse question we can ask, if can we say that T square is compact, implies T is also compact. In fact, the answer is no. Okay, so let us look at the following example. So define T from L2 direct sum L2 into itself by T of xy as y comma 0 for every xy in L2 space. Then we can show that T square of xy, that is T of y comma 0, this is 0 0. So that means T square is a 0 operator, so which is compact. But T is not compact. Okay, so to show that T is not compact, let us look at T star T. So for that we have to find what is T star T. So T star, to find T star, let us look at this equation. Some ZW here is inner product y comma 0 ZW, and this is nothing but inner product y with Z only. So this is nothing but, so you want to express this as inner product x with y with something. So this is actually T star of ZW. Okay. So this can be obtained only with so this, if this is, so y inner product with Z can be written as xy inner product with 0 comma Z. So that means T star of ZW is 0 comma Z for every ZW in L2 direct sum L2. So therefore, so if you look at T star T at xy, this is T star of y comma 0, but that is nothing but zero comma y for every xy is coming from L2. So T star T restricted to the space 0 direct sum L2 is exactly identity operator on L2. You know that on an infinite space, identity operator cannot be compact. So T star T is not compact, hence we can say that T is not compact. Okay. So here we also use one observation. If T is compact and M is any closed subspace, then we can say that T restricted to M, it's a map from M into H. This is compact. Okay. So these are some of the important properties of compact operators. In the next class, we will discuss more information about compact operators. I'll stop here. Thank you very much.